Okay, what I want to do today, good morning everybody, is to discuss the role of representational theory of measurement. According to Luz and Suppes, representational measurement is on the one hand an attempt to understand the nature of empirical observations that can be usefully recorded in some reasonably unique fashion in terms of familiar mathematical structure. Well, you know the stuff, so I will just skip. Suppes' beautiful example of measuring weights by means of a balance, as represented by a suitable set-theoretical structure, suggests that RTM, representational theory of measurement, involves a claim about measuring procedures, perhaps a form of instrumentalism, and that every measurement procedure consists of constructing some homomorphism. Curiously enough, other authors have got the impression that set-theoretical structures RTM makes use of, far from representing empirical measurements or empirical instrumentalist measurement, are not even about the natural world. For instance, Michel writes that RTM is based upon an inconsistent triad. First, there is the idea that mathematical structures, including numerical ones, are about abstract entities and not about the natural world. Second, there is the idea that representation requires at least a partial identity of structure between the system represented and the system representing it. And third, there is the idea that measurement is the numerical representation of natural systems. The second and third ideas imply that natural systems instantiate mathematical structures, and when the natural system involves an unbounded, continuous quantity, it provides an instance of the system of positive real numbers. Thus, the second two refute the first idea, the principal raison d'etre for the representational theory. Now, let me start by distinguishing between metrization and measuring. By metrization of magnitude m, I understand a demonstration out of empirically meaningful conditions of the fact that m is measurable. RTM accomplishes the metrization of m by building suitable set-theoretical structures and proving the existence of a certain homomorphism, which is a mathematical representation of m. By measuring procedure, I understand a procedure for actually finding the value of m for given objects with respect to a unit of reference. It seems to me that RTM does not claim that every measuring procedure consists of explicitly constructing some homomorphism. What it does claim is that any magnitude m must satisfy certain conditions in order for it to be metrizable. The task of the theory of fundamental metrization is to probe into the conditions that m must satisfy in order to guarantee the existence of such representation when the same does not presuppose any other previous metrizations. The fundamental measuring procedures determine specific empirical procedures for qualitative comparison of the specific property involved, and chooses a standard with which the assignment begins. It is certain that RTM has never maintained the claim that mathematical structures, including numerical ones, are about abstract entities and not about the real world. Clearly, mathematical structures are abstract entities insofar as they are set-theoretical structures. And they are about the natural and the social world, let me add. But the meaning of about, in this context, needs philosophical clarification. I will try to clarify the idea that natural systems instantiate mathematical structures and criticize the idea that natural systems may involve unbounded continuous quantities. It will be seen that the existence of important metrizations in economic theory requires the adoption of rather severe restrictions. Let me start by making some distinctions. I distinguish target, concrete, real systems, let's say the US economy 2012, given in pre-theoretical experience, from model systems on one hand and set theoretical structures on the other. I take for granted that scientific theories can be identified with certain ordered classes of set theoretical structures. Moreover, I assume that theories can be formulated by means of the definition of set theoretical predicates. The relationships between target systems, model systems, and set theoretical structures is roughly the following. A model system is an idealized replica of a certain class of target systems, a replica that can be described by means of actions defining a set theoretical predicate. Model systems are not set theoretical structures, but rather imagined physical, economic, or geometric objects that represent their corresponding target systems. Thus, model systems can be seen as imagined physical systems, that is, hypothetical entities that, as a matter of fact, do not exist spatio-temporally, but are nevertheless not purely mathematical or structural in that they would be physical things if they were real. If the Newtonian model of Sun and Earth were real, it would consist of two spherical bodies with mass and other concrete properties, such as hardness and color, properties that structures do not have. Likewise, the populations in the Lotka-Volterra model would consist of flesh and blood animals if they were real. And the agents in Edgeworth's economic model would be rational human beings. Hence, I think it's important to stress that the representation of target systems by means of a model system, of a target system by means of a model system cannot be identified with any kind of homomorphism, since homomorphisms are mappings from one set theoretical structure into another. My version and defense of RTM is grounded upon these distinctions. When the question arises whether the property of components of a given type of concrete system is measurable, RTM proceeds to build a typical model system to represent the class, and based upon the properties of such model, builds a class of set theoretical structures by means of the definition of a set theoretical predicate. It is in this sense that mathematical structures are about the natural world. They are true of more or less idealized model systems that purport to represent some type of concrete target system in the world. These structures, insofar as they represent target systems, may be called empirical structures. Pat's famous example of measuring weights by means of a balance is a classical instance of an empirical structure, or so I think. But it can be misleading in two ways. It may suggest both that measurement structures are always empirical, in the sense that they are not describing idealized model systems, and that RTM is a general theory of concrete empirical measuring procedures. The main criticism against RTM in the field of economic methodology begin by misconstruing it as a theory of measuring procedures, which it is not except for some cases. It is a theory about the conditions and properties of certain classes of target systems must satisfy in order to be measurable. It functions thus as a sort of ideal control for empirical measuring procedures that can also be suggestive of empirical measuring procedures. A natural or social system, that is to say a target system, instantiates a mathematical structure if and only if it is exactly described by the actions defining the structure under a certain empirical interpretation, without the mediation of a model system. In such a case, the structure may be called an empirical structure, in a strict sense. For instance, a structure of the form X with a reference relation would be an empirical structure faithfully recording the preferences of a given consumer if X is interpreted as a collection of consumption menus over which the consumer has to make a choice, and his pairwise preferences are correctly recoded by the relationship. But then nothing guarantees a priori that A will be a weak order. It doesn't have to be a weak order. In general, it is not target systems the objects that are exactly described as mathematical structures,